my PhD thesis 6-7 years ago. Was supervised thesis was the University of Girona, and so one of my supervisors was in Spain, and the other supervisor was Professor Giovanni. I was applying a theory. I'm going to talk a little bit about this theory during my presentation. It's model interval analysis applied to robotics, control engineering. When I finished my PhD, I completely changed field. My research, I started working on biomedical engineering. So I spent 1 year in the US in the University of California in Santa Barbara, and they were like working on biomedical applications like artificial pancreas. It's going to be the topic of my presentation related. So let's start. So this is a joint work that we did like a couple of years ago. So I wasn't working with interval analysis, so I completely stopped working. But Luke contacted me and he told me that he had a student that he would send me this student like he was 6 months. And he said, yeah, that's great. And let's try to do something related to applying interval analysis to what I'm doing now, biomedical applications. And we came up with this idea. So the title of the presentation is Robust Set Membership Parameter Estimation of the Glucose Insulin Model. So we recently submitted this work as in a journal. Let's hope it gets accepted. Just to mention that funded by the Wellcome Trust is a charity, a big charity here in UK. So a little bit the outline of my presentation. So I'm gonna put in context my work. I'm gonna talk about diabetes management. Then I'm gonna introduce what's the glucose insulin minimal model. That's the one that we're gonna identify later on. Then, to motivate why it's interesting to identify this model in a robust way, is I'm going to present an application to robust fault detection that we did some time ago with the colleagues from Girona. Then I'm going to introduce the methodology of set membership parameter estimation, the algorithm that we are using, the algorithm developed by my group that's CBS, set inversion with interval analysis. Then I'm going to present how we apply this algorithm to the problem of the set membership parameter estimation of the minimal model. And at the end, I'm going to talk a little bit about this theory, model interval analysis. This theory that we developed, well, I didn't develop, I was using it in Girona, was a collaboration between University of Girona and University of Barcelona. How we can use this theory to reduce one of the big problems we have in interval analysis, the overestimation of the results. So we're going to see how we can use. And finally, I would like to present a nice implementation of the CD algorithm in my lab that, well, we will see that it has some interesting properties. I'm going to show the final results. So let's just start putting in context the work. Probably some of you already know these concepts, but diabetes, it's a big problem. The definition is a group of metabolic diseases characterized by high blood glucose, high blood glucose, and we can differentiate between different types. There is type 1, that is when your pancreas, the cells in your pancreas don't produce insulin, so it's an autoimmune process that destroys the beta cells. So you need exogenous insulin. There's type 2, that is the most common one, that is related to lifestyle, like obesity, lack of exercise. It's when your body is resistant to this insulin. So you produce insulin, but your body is saying, no, that's not enough, so you need more insulin. And at the end also, it can, at the end also, your pancreas can say, okay, sorry, I'm not able to produce this insulin, and also stops producing insulin. And finally, the gestational diabetes is more related to hormone levels, but also you're resistant to these insulins, pregnant. Symptoms of diabetes: frequent urination, increased thirst, increased hunger, and that's the big problem. Complications, like if you keep these blood glucose levels very high for a long time, then you can really nasty complications like heart disease, kidney failure, damage to the eyes. Just some numbers, like 382 million people in the world have diabetes, and it's increasing. It's increasing a lot, so it's really an epidemic. 5% of them, 5% of the population, so it's massive. US, you know, now China that they used to have now is also becoming a big problem. And 90% of them are type 2, so it's related to the lifestyle. Type 1 is like a little bit of a mystery. They still don't understand exactly why it happens. They are still trying to figure out what happens with them. Okay, then how we treat diabetes. Type 2, there are some drugs, some oral drugs to improve this insulin sensitivity, so to get more sensitive to this insulin. But once these drugs don't work, or in the case of type 1 that we don't produce insulin at all, we need then insulin therapy, so insulin injections. We see the first injections, intravenous injections, 1933. Then 1980, we got like the insulin pens, like subcutaneous insulin delivery. And nowadays we have these cool devices, the insulin pumps that like continuously use insulin. Big problem we have, if we over deliver insulin, then we have what is called hypoglycemia, or blood glucose levels go very low, we feel dizzy, we can faint, and we can even die of hypoglycemia. So it's very important to control the blood glucose levels in a tight range. Okay, and then that's the application that I'm working on is, we call it artificial pancreas. It can be called in different ways. It's a closed loop system, but basically what we are trying. So recently we also got, apart from the insulin pumps that continuously deliver insulin, we got a new technology, maybe 7 or 8 years ago, that is a continuous glucose sensor that measures glucose levels every 5 minutes. So then, if we have a glucose sensor and an insulin pump, what we can do is we can close the loop. A closed loop system to control blood glucose levels. Sounds easy? It's not easy at all. It's very complicated. Why? We have uncertainty everywhere. Human body is completely uncertain. Variability is massive. Errors in the glucose sensors are very big. Delays. So it's a really complex control problem. So well, we are not the only ones working on that. There are like several groups around the world working on that. The one in Santa Barbara, where I spent 1 year, were one of the pioneers in this work. So, but we took a completely different approach. So, other groups, they use like more a classic control engineering approach, PID control, MPC control. I started working in this group at Imperial College London, that they have this particular approach that is called a bio-inspired approach. So what they do is like they try to mimic biology and try to solve problems like mimicking other biology. There is a very successful story. Professor Christopher Tomasu is the head of the Center for Bio-Inspired Technology where I'm working. That he's one of the inventors of the cochlear implant. I don't know if you've heard. Like it's like a microchip implanted in the brain. Like it's mimicking what the hearing is doing. So they managed to replicate, to recover the hearing. So now you have like deaf kids that get this chip implanted and they recover the hearing, which is quite impressive. So we are trying to apply this same concept to different biomedical problems, and one of them is like the bio-inspired, what we call bio-inspired artificial pancreas. So we try to mimic the behavior of the beta cell in the pancreas that produces insulin, and try to see how it works and try to apply that to the artificial pancreas. Another characteristic of our group, or particularity, is miniaturization. We are really good at putting things in very small microchips and making things really low power and really cheap. So that's another characteristic. That's just all context. So here we just see one picture of the implementation of the bio-inspired artificial pancreas connected to a glucose sensor. The sensor, the microchip also can go incorporated in the insulin pump. So that would be the ideal solution. Now it's fine. Device. And here we can see we've been now 3 years doing clinical trials. Things are going really well. I'm very happy with the results. We recently published the results in a good journal. And we are moving forward. Now next step is going to be exercise. Exercise plays a big role in glucose management, has a big impact in glucose levels. Different times. And then the next step is going to be ambulatory, so going outside of hospital. Now is everything in hospital. Next step is going to be real life conditions, which are challenging. Okay, then now let's talk a little bit about the project, well, this work about identifying the minimal model. So what's a minimal model? Minimal model is one of the models that is used in diabetes technology to model the dynamics of the insulin glucose system. Why we call it minimal? Because it's like the minimal number of compartments, what we call compartments or equations, that we need to model these dynamics. So we have more complex models, like with 10 differential equations, like 30 parameters, that are like more low level, but then you have massive problems to identify. So you need what is called basements, like radioisotopes to get the different fluxes. So we are not interested. We want like a minimal model because we want to identify with the normal data that you can get from a normal chemical glucose and insulin levels. So here we can see a schematic of the model. We have the two compartments, the glucose and what is called remote insulin, like an auxiliary compartment. We can see the liver, the peripheral tissue, that is the muscle, and plasma insulin. And we see all the fluxes. So we see that the insulin affects the liver and stops the glucose released by the liver, then also improves or promotes the glucose uptake by the muscle. So we see all the fluxes of glucose and insulin. So this model is used, like the main utilization of this model is to identify metabolic parameters like insulin sensitivity. Basically tells you how sensitive you are to the insulin. And insulin secretion, so how good also is your pancreas at secreting. So like typical medical applications of this. We need to reparameterize the model. You see the fluxes we reparameterize like with P1, P2, P3 to make it identifiable. And we now we get this with this form. We have 3 parameters and an additional parameter that is like the initial glucose value. So it's like it's what I said. We have like different parameters that are interesting for the clinicians, like insulin sensitivity, glucose effectiveness, and then we have like other applications of the minimal model, like in the diabetes technology community, that are like, for instance, hypoglycemia prediction. With this model, we can forecast glucose levels in the future, and we can predict if we are going too low. Also, we have like some people use it for a model predictive control, also to forecast to optimize the fall detection. That's an application we worked like 3-4 years ago that I'm going to present now, and also for simulators. So you can have a simulator where you can test your controllers before you go to clinical trials. You can test it in a simulator. Okay, the application I was talking about, robust fall detection. So you keep here we see the minimal model, but also what we need is 2 additional models in order to model the dynamics of insulin absorption. So when we inject insulin subcutaneously, there is like dynamics to absorb this insulin to the plasma. And the same for the carbohydrates. When we need a model that models the absorption of carbohydrates to the bloodstream. So these models are independent, so we can identify them independently because we measure. So we have the inputs, and we measure this one and this one and this one. So no, sorry, we have this one and this one. But now we are going to focus just on today we're going to just focus on the identification of the glucose insulin. So the application to fall detection that we did, we published this paper in 2012. So probably I don't know if you are familiar with the concept of analytical redundancy. So basically what we do is very simple. We have an artificial pancreas, you see here, that's this bit. And then we have a reference model. And what we do is we compare the output, the measured glucose of one subject with a reference model. That in this case is the model that I showed you before, minimal model plus the absorption models. Then if we see that there is like a big mismatch between what we measure and the model, what we are predicting, then we can see that something is going on. For instance, in this case, what can go wrong? the insulin pump, an occlusion in the insulin pump. We are telling the insulin pump deliver that much, and that's quite common. So we've seen that many times in clinical trials. Like the catheter gets like there's a plug in the catheter, and we need to stop the trial. So having a system like that is really interesting in this application. And glucose sensors are also like very unreliable, so they can fail. So it's interesting to have like a fall detection system for an artificial pancreas. So here we can see some results of this work. Here we can see in red we can see an interval like this, the envelope encompassing the glucose measurements. The sensors, as I said before, are very unreliable, so they can like easily 20% error. So that's one of the problems of this application, like uncertainty variability. And in green we can see the estimation that we do with the minimal model plus the here we see that we have a palm occlusion, and we see that when we have the no intersection between the envelope of the glucose measurement and the envelope of the estimation at this point. We tried that like in a simulator. It's like a NDA simulator, and it works pretty well. And we still didn't try it in clinic. That's one thing we have in the pipeline. Okay, then let's talk a little bit about cell membership parameter estimation. Probably you already know some of these concepts. So the typical approach to identify the minimal model is like the typical least squares technique, weighted least squares if you want. So basically what we are doing is we are minimizing the error between the measurements and the model. Some people use like Bayesian methods, like sometimes you have too many parameters and you need to have some priors of the probability distribution of the parameters and balance details. We took a different approach because we want like robust applications, so we want to use like a cell membership approach. So what we are doing is basically we assume that we have a bound on the errors of the measurements. So the measurements are like encompassed by intervals. And basically what we are saying that we want to find the parameters for model X in this case that are consistent with these measurements. So all the models that are crossing these intervals representing the measurements. Same this equation here. So it's quite simple the concept. What we are using to solve this problem can be solved by the algorithm called cell immersion linear interval analysis. Here is a very simple example of this problem. We have this problem here that basically we want to find the parameters x, y in this initial space. So we have this initial box where we want to find our parameters such that this constraint is satisfied. So this equation here is inside this interval. So basically the CV algorithm, what it's doing is evaluating this function using intervals and testing this inclusion. So if this inclusion, this evaluation is inside the interval 1, 2, then it's a solution, that is the red area. If the intersection is empty, then it's no solution, it's the blue area. And if we cannot prove this one or this one, then it's undefined. And in order to stop the algorithm, we need like a precision. We need to define a precision absolute. So when the width of the box that we are dissecting is smaller than epsilon, then we say that is undefined, that is this yellow area. So that's the basics of the CV algorithm. So we use CV to identify our model, the minimal model, and here is the problem. So we have 4 parameters, we have 4 intervals. We took the intervals for these parameters from the literature, so there are papers studying like the minimal model, so our population values, we know the ranges of these intervals, these ones here. Then what we did is we did like a simple Euler discretization. I know we could use like more sophisticated techniques for all the integrations, but here we don't care about the small errors. With the errors we have the measurements, So the errors we do in the discretizations are like negligible. So we can we have this hypothesis that the discretization of modeling errors are already taken into account in these models. Okay. So well, that's a statement of the problem. And what I mentioned before, so I wanted to talk a little bit about this theory of model interval analysis, just like the main idea. Just I wanted to mention that we recently published a book about the theory. It took us many years. So you can select this reference here. And also there's like a software that is available from this link, or if you send me an email, I can send it to you. So that allows you to use the theory, because the theory can be very nice, but if you don't have like algorithms to use the theory, is quite useless. So that, like the main problem, that the difference between model interval analysis and classical interval analysis is that we can solve problems of this type. So we can have quantification of the uncertainty. So like that's like the problem we saw before, that we can solve with CV algorithm. But in this case, if we see, we have like the universal quantifier and the existence of quantifier. The basic CV algorithm cannot solve this problem. So I'm not saying that there are other ways to solve this problem, but model interval analysis is one way to solve this problem. So that's like general idea of what's model interval analysis. But in this problem, the parameter identification problem, we are reducing this property of model interval analysis. We use another property that is like how to reduce the problem of overestimation we have in interval computation. And that's just one of the results of the theory. And well, we can define something particular of the model interval analysis. Is what we call dual operator. That basically what it's doing is inverting the bounds of the interval. So we have like an interval AB, we apply dual operator, and we reverse the interval. Then we apply what we call the B transformation. I'm not going to explain the whole theory, it's just like that. The basic concept of what we are doing to reduce the overestimation. Now basically what is doing B transformation is applying the dual operator to the instances of the variable, of the variables, when the monotony sense of the function with respect to the instant, so we have one variable, multiple incidents of a variable inside the function. So when the monotony sense of the function with respect to this instant is contrary to the monotony sense with respect to the variable, to the whole variable, so we apply the dual operator. So here we can see a very basic example, like a trivial example. Well, the main characteristic of the property of this transformation is that we keep this inclusion. So that when we apply the transformation, this is an inclusion function of the range of the function. That's of course very important. So let's assume this very trivial example that we have x minus x, this interval. So if we apply the basic natural interval extension, we obtain the interval minus 2, that is of course overestimated. And if we rewrite this function with, we would like differentiate the instances like x1 and x2, and we calculate the monotony of the function with respect to x, the whole variable, and with respect to each one of the incidents. So we see that one of them is like contrary to the sense of the whole variable. So if we apply this D transformation, we apply the dual to the second incidence of the variable, and we can see that the result that we obtain is like the range of the function. I know it's very trivial, but it's just to get the idea of what we are doing. So we applied this, well, we also did some symbolic manipulations to the minimal model in order to get rid of some of the incidents, and the ones that we couldn't get rid of, we applied the D transformation. So we can see that we applied the dual operator in some of the instances of the variables. Then, in order like to do the identification, of course we need data. Then we took data from like a standard test that is done like in clinic that is called the intravenous glucose tolerant test. But basically what it does is like it gives an injection of glucose in fasting conditions and it measures like predefined intervals, plasma glucose and plasma insulin. Then we assume glucose errors. This is plasma, so it's laboratory testing, so that the errors are much smaller than like with the continuous glucose sensors. So we assume like a 4% error in the glucose, 1% error in insulin. Then also we eliminate 5 of the initial values because this model like is a simplification of course and is not able to like represent the dynamics, the initial dynamics, the initial increase of glucose. So we eliminate, that's a standard, so everybody is doing that, eliminating these 5 initial glucose values. And also then what we do is we relax the problem. So we say that the 3 of the points, we don't need to satisfy 3 of the measurements. It's what is called like a Q intersection. So it means that the model doesn't need to cross 3 of the points, because if not, it's very likely that we don't have any solution. So that's also quite a standard in cell membership parameter estimation. Okay, then the algorithm that we use, as I said before, is the CBIA. So when I was doing my PhD, I was using C++ all the time. But then when I started working with this technology, everybody uses MATLAB. So I kind of forgot everything about C++, and now I'm using just MATLAB. Problem I had is like CBIA in MATLAB is like extremely slow. It's like horrible. Try to implement the CBIA algorithm in MATLAB, and it's like orders of magnitude slower. Impossible. Yeah. Okay, then I don't know how one day I came up with this idea. So now I'm quite familiar with MATLAB. I know MATLAB is really good at working with vectors, with matrices. And I said, why if we implement CBIA in a way that MATLAB is good, using like vectorial computations? Then the idea of the algorithm is like, that's like the classic CBIA algorithm. So we have like an initial box, we evaluate, we bisect it, we take one of the boxes, we evaluate, we bisect it, and so on. So we have like a list, we put the bisected boxes at the end of the front of the list, doesn't matter, and we keep going. Then the idea of like the VCDA, the vectorial CDA, is like, okay, we have the initial box, we evaluate, we bisect, and in the next iteration, instead of just taking one of the boxes, let's take both boxes and bisect and evaluate both, the 2 boxes at the same time. So we all this, you can do that in MATLAB by using vectorial computations. What we do is we implemented a vectorial interval arithmetic, then all the functions of the CBIA algorithm are like vectorial. The bisection, the evaluation, the inclusion function, everything is vectorial. Result, we can get an implementation of CBIA in MATLAB as efficient as C++. So some people, when you say that, they don't believe in this. That's not true. It's true. Can prove it. And then there's another interesting point of this implementation that we didn't do because we really don't care about calculation errors, floating point errors in these kind of applications. But that's an idea I had that I think is quite interesting. That one of the, like changing the rounding mode, when we care about the rounding mode, the truncation errors, changing the rounding mode is quite computationally expensive. So in this case, we need to change the rounding mode less times, because every time we, per second, we evaluate the whole vector of boxes, it's like just one time that we round the mode to compute the lower bound, and one time for the upper bound. So that was quite, I think it's quite interesting, as something I would like to investigate. Probably it's a nice work. Okay, just like a simple example to see the efficiency. That's a paper that, so the implementation of this vectorial CBIA was published in Reliable Computing a couple of years ago. Just like one simple example, we see this torus function, and we see like the classic MATLAB implementation, 336 sevens for this precision, C++, and the MATLAB VCDA implementation, same time. So, you mentioned that also we can incorporate within that. It's not very tested, so it's still like a work in progress, like vectorial contractors. So we can also apply the same concept to contractors, which is quite useful. Not always. In this case, for instance, we don't increase the computation time. I will only reduce the computation time. Just like to show you how it looks like the code. That's the code for this problem, for Notorious. So we define, that's Benoit Delano, the student that Lucen was really bright and good at programming, and he did an amazing job at implementing these tools. So that's how you define the problem. You define the type of problem, box, interval, epsilon, and you just input your function on that, and that's it. And well, and finally, the results of using the BCD algorithm with everything I said before to the problem of identifying the parameters of the minimum model. So you can see, like with this computer, the main limitation here wasn't the computation time, was the memory. Okay. I mean, for the memory precision was 0.01 epsilon. The memory that you need for this problem is massive. So we needed like a server with 96 gigabytes, and it took us 13 minutes to get these solutions. I chose the minimum epsilon that for which we could find a solution. So these red dots are the solution. Here we can see the boxes of an inner approximation of the solution and the box for an outer approximation of the solution. So these are the different planes, E1, E2, for the different variables. And just for curiosity, what happens if we don't apply the difference formation of model interval analysis? So it's 3 times more computation time to solve. So it's kind of work using interval analysis for this problem. And just to show you then the simulation with these parameters identified, the inner approximation and the outer approximation of the parameters. Thank you very much.
Okay, time for questions. Small question. On your slides before, where you show your results, here, what is interesting for you? To draw the set or just the smallest box?
You mean the
Yes.
outer box, the one encompassing the...
Because you draw here some projections.
Yeah, these are the projections.
So it is interesting for you to get these projections.
Well, that's just visualization. What is interesting at the end is we want, for instance, for robust fall detection, what we want is this outer box.
Okay,
So for we do the blue envelope.
So maybe it would be more efficient just to compute these 2 boxes.
Yeah. So yeah, and that, when I did that, I wasn't thinking about the application of probable.
Okay, just
was just
okay.
the
Yeah,
problem.
just to illustrate
Yeah,
your
but
vectors.
of course you don't need any approximation for the robust fall detection application. Depends then for what you want. If you just want to find one solution, then you don't put it with the linear approximation.
And I have also another question. Of course, I use MATLAB often for my training, and I understand that sometimes when you vectorize, you do much quicker. But I have no idea, you understand, why it's such, why you have such a difference when you do vectorization. There is something else, there is no prioritization.
No. But Linux MATLAB has very efficient C or Fortran implementations inside. And what MATLAB is really inefficient is at calling functions. So when you use a classic C algorithm, you call thousands, millions of times a function. And it is not efficient in MATLAB because it's not a compiled language. It is, I think, the main reason.
Here in your implementation, it uses only 1 core or 7 cores?
Well, this server I think has 4 cores or 8 cores, but we tried the parallelism and it doesn't make a big difference. So it's not the parallelization. MATLAB has a toolbox for parallel computing. We tried and we spent some time and didn't get an interesting result. So it's not the parallelization.
Sure.
So yeah, this web toolbox is available on website, so everybody that like analyze documentation. So if you want to use it, you're more than welcome.
Other questions? Yes.
I'm wondering about the dual operator that you defined in order to avoid overestimation. Is that dependent on the degree with which a variable occurs in the function expression?
You mean how many times?
Yes, well, either the degree at which the thing occurs in the expression of the function, or how many occurrences of that variable there are in the expression. Because if you
Depends on the monotony. So if the function is monotonous with respect to the variables, then you can apply, it doesn't matter how many times the variable appears in the function. So if the function is monotonous with respect to all of the incidents and you can apply the rules, then you get like the...
So you're relying on the monotonicity of
Yeah,
the function.
I mean, that's the main limitation. That of course if it's not monotonous, then usually we have an algorithm that we call fstar that what it's doing then is bisecting the intervals and computing for each one of the intervals and then doing the joins of the results. So it's like a branch and bound algorithm that computes an approximation of the range, like with like branch and bound and then applying the dual operation.
There is another technique, there's slight variation of interval arithmetic called finite arithmetic. I don't know whether you've come across that. That also helps keep
So as I said, this one way, Taylor series, and there are many ways to get like better approximations of the range. I'm saying that it's the best one, just one. I'm using it because I use it during my PhD. Well, that's another thing we had in mind is like to incorporate InLab in this unit. So I'm pretty sure that we can use InLab, the arithmetic in InLab.
Are there any copyright questions? Because InLab was created by people when they are selling it at the moment.
I think if it's for academic use, it's free. Not anymore.
Not anymore. I saw a room last week.
We recently paid last year 40-something €5 or pounds, I can't remember, per personal use of the demo.
Cheap.
Yeah, cheap, but to pay.
Well, that's something I had in mind to contact
It's not possible.
like to try to fuse this implementation of CDA with InLab because I think that would promote a lot the CDA. Here we don't have like a roundings, so we didn't implement rounding because it's something quite complex, it's machine dependent, so we didn't want to spend the time. So we have like a simple vectorial interval arithmetic without the, it's model arithmetic. Model arithmetic is slightly different.
I think InLab is for direct interval computation, whereas CDA is for inverse computing, inverse the reciprocal of the set, which is solving the problem, and so they are not comparable. CDA is another layer upon a interval computation technique, and here you are using your own implementation that you all to have used InLab. But we would have to program CDA or vectorize CDA upon InLab. Maybe we can compare InLab to C++ to blocks like a graphic class or Phi++.
Yeah, sorry. Just a quick question. So you're using this set the membership parameter estimation in order to characterize to estimate your parameters for your model, and those you're going to use them for something else, right? So it's in, I mean, the way I see it is somehow it's in the interest of the problem that you're going to use them for to try to be guaranteed somehow. That's somehow the whole point of this, right? So I don't really get why would you just use Euler method instead of using just already standard techniques for all these. I can see the point that you're saying that that your sensors are somehow the uncertainty, but you're using lab data to estimate your parameters. So I would think that you want to be as guaranteed as possible somehow.
I think the problem with all these available software tools for the qualitative interaction is that I think they're not very efficient when you have uncertainty in the parameters.
Well, actually, in terms of that, in our group, maybe we can talk later, but we kind of work in these kind of problems, and we just recently, I think Nolgo's collaborator was, we presented something for parameter estimation with Taylor models actually, but we're solving like kind of challenging problems that we couldn't solve before.
Yeah.
But so we have all these kind of techniques of all these implemented. But it was just mainly a question of if you're, I didn't really understand if you were using lab data, why wouldn't you like kind of be
Well,
using
because we really don't, and we did some tests like simulation to see the error that we do because of the discretization. It's like it's nothing compared to the errors we that come from the sensors and other.
even compared to the ones with the lab data, which is the one that, which is the data
Yeah.
you're using for the
Yeah, if it's 4% error here compared to the rounding mode, it's massive. So, but yeah, I mean, I'm not saying that one of these warranty techniques would be.
Because at some point when you were, since you were mentioning the error of the sensor, I thought somehow that you were doing this online or something like that, but then when I heard that you were using the data from the lab, that's when I actually got the question.
Well, that's something I didn't say. The motivation of this work was because first we did the fault detection application, and when we had to decide which uncertainty we put in the parameters, we had no clue. So then we need to identify in some way like the parameters using the standard version approach. So we did the opposite. The inverse. We came up with this idea.
So you include in your intervals of parameters the uncertainties, no? The model uncertainty in such way that your model will contain every possible real behaviors, no? So you take into account in your parameters. No? This is why how you calibrate
I have to say that this is a little bit ideal what I'm saying here, because in real life, so these parameters are not constant. So insulin sensitivity, for instance, is the variability of insulin sensitivity is huge. Just like it's called circadian rhythms. Like it's not the same in the morning, in the evening. You do exercise, it changes, and you should identify this insulin sensitivity for different scenarios. Then, of course, that's like standard conditions, like in clinic, fasting, resting. Then, of course, in real life, this insulin sensitivity parameter maybe is much bigger, or you need several.
for the fault detection, you use your model using direct test or inverse test. I mean, you propagate, you compute the state of time k based on the state and the
So it's like
so it's direct
normal
test, yeah?
simulation. Yeah.
And you use least square to identify the model now.
When you
Least square identification least square now.
for the minimal model.
For the
When we did the model
for fault detection.
for fault detection, yeah.
And you use this
Well, we took kind of we did least square, you're right, and then we just put uncertainty.
calibrated, yes. But when you use
10%.
this model in a direct test in order to compare the output of the model with the real measurements, when you propagate, when you compute the x time instant k, you inject the measurements. So x time minus 1 is not the output of the model time minus 1, it's the measurement. No?
It's a measurement. So
if
we
you inject,
initialize the simulation from the measurement.
if you inject measurements, your model will follow the fault at the end. So you cannot, you have only small.
But we have a time window. So that's I'm sure you're familiar with.
So it's something as a in between simulation and prediction. So it's called observer.
You're familiar with Joachim Armangol's work.
So yeah.
So it's that. I was working with him.
Yeah. Thank you.
Any questions? Maybe a small question. Just to go back to the comments on the solving the differential equation. It is true that for your application for identification, I do agree with you, the uncertainty is so large and the integration time step quite small. So yeah, I think it's okay to use other method. But then the comment is interesting because if you are trying to do some fault detection, prediction, like when you said predict hypoglycemia, you have to run your model like an open loop with no measurement available for and maybe at that moment
It's 3-4 hours.
time step duration time horizon would be large enough, and there might be some discrepancy between what you actually compute and the actual solution, even though the models, I don't know the model, but maybe it is not so steep or so difficult to solve still. Maybe at that on this given issue of prediction, it might be interesting to use proper guaranteed set integration techniques for
So that's something that maybe we'll consider behind today.
maybe another comment. This is the projection of the parameter solution set. And okay, I was preparing the question, but then you said these parameters vary with time and with the circadian cycle and also with the person and so on. So when I see computation time, I am quite curious about, is it an issue, 30 minutes to adapt to the, and also interacting on 12 cores on an embedded system. How do you imagine the future? How do you imagine a solution to adapt? Maybe it's not.
To use that in real time.
Yeah.
Yeah, that's hardware.
Yeah. I don't know. It's really
At
interesting.
least this version. Yeah, we're in no way use that. But well, maybe you can, it's something you can do offline. So once you have like a retrospective data, you do it offline for the next stage. So it doesn't need to be, because what is interesting is like you're going to use these parameters for the next stage. So maybe something. Or maybe you can like, you collect data, you do apply that offline, and then you have like a library set of parameters for different, for morning, for exercise, for different scenarios. That's how I suggest it how you can use that.
And also, I was thinking about the shape of the sets or their projection. And you have if you embed the yellow boxes in an axis aligned box, that is the outer approximation, you will introduce a huge over approximation.
Yes.
And if you map this over approximation onto the output, you will have spurious uncertainty. So is this an issue?
Well, this envelope I'm showing here, the blue one, is not like the simulation of the model with the, it's the simulation of all the boxes.
It's the head of
and
the
box.
yes. But this cannot, it's not optimal on an embedded system because it is time
It is
and
time
energy
consuming.
consuming. So do you have an idea of how to solve this? Oh no, is it an issue or? I ask all these questions because I'm just,
No.
of course.
That was
I don't know if, so within, guessing you're aware of like multi-parameter programming, so you can map these parameters to be in the state space and then use the particular parameters depending on what things you're measuring in real time and then you can use and small intervals with it. further embedded chips as well.
Yeah, familiar with that. So yeah, standardization, of course, is essential.
Discussion. Also, you mentioned that for detection or something going wrong detection, that there is, of course, delay in the detection. Do you think this delay can be an issue for artificial language pathways?
For the panel occlusions, we need hundreds of tests. So we have this simulator that is FBA, medical regulation body in the US, that they released this simulator. So you have like kind of real dynamics, and we did the tests, and for these delays we have like an average delay for the detection of a panel occlusion of maybe 2 hours. It's quite long because the dynamics are very slow in this problem. But even with 2 hours delay in the detection, the glucose levels that we were reaching were dangerous.
Okay.
So we're like acceptable. It's not like I go to 500 milligrams, that is like critical. No? It's like 200 that is okay.
Other questions? Okay, yes. Thank you, guys.
Are you working also with the Aerospace Institute in Berkeley, London? Because I'm working on 2 trials monitoring, so we are integrating some sensors on plane on a wing, and we are monitoring the state of the structure. So maybe for detection, probability of detection, we are working on it, on these areas. Maybe we can
Yeah, and we don't have a collaboration.